Mode of transfer of heat. Now see, in the present lecture we are going to start with the topic how the heat is transferred from one region to another region. Okay. Now we have seen in the fundamentals that spontaneously heat flows from the region of higher temperature to the region of lower temperature. Spontaneously means by itself, that is no external energy or work is needed. So if heat is allowed to flow by itself, then it's obvious that it will flow from the region of high temperature to the region of low temperature. Got it? Now when you see what are the different modes, what are the different ways in which the heat can flow from one region to another region. So basically we have three such ways. Number one is the thermal conduction. Now see, conduction is a mode which takes place in all the three media, all the three states: solid, liquid and gases. Okay, so medium is a necessity for conduction. Clear? Medium is a necessity for conduction. Conduction is one of the mode for the transfer of heat, and when the heat is getting transferred by conduction, so medium is the necessity. That is, conduction cannot take place in vacuum. Got it? Conduction cannot take place in vacuum. Now the second mode which we will explore is convection. Convection is basically the mode which takes place in fluid, that means the liquid and gases. And since again fluid is necessity, so medium is required for convection too. Convection cannot take place in vacuum. Okay, so these are the two modes which you can see. These are the two modes which require medium. They can't take place in vacuum, not possible in vacuum. Okay, and the third mode which you will study is the radiation, or better say thermal radiation. Now when you will see thermal radiation, you will see radiation is basically electromagnetic wave, and for the transmission of electromagnetic wave no medium is required. So radiation is a mode which can take place in vacuum also. I repeat, radiation is a mode which can take place in vacuum also. So anytime if you need to answer which mode of the transfer of heat is possible in vacuum, so that is radiation. Okay, and in radiation the heat flows as a form of electromagnetic wave. Got it? So this is the introductory subtitle, subheading, mode of transfer. There are three modes: conduction, convection, radiation. Conduction and convection require a medium. They cannot take place in vacuum. Radiation can also take place in vacuum. Now let's see, if you want to visualize all the three modes together. See, there is a container in which there is water. Okay, and you are just giving heat to the water. So see, this is the radiation mode. See, the energy, thermal energy is passing through the container and no medium is necessity. So this is the radiation mode. If you hold the handle of the container, you will feel the heat. When you are holding the handle of the container, you will feel the heat, it get heated up. So heat energy from this boiling water get transferred to the handle. This transfer is what? Conduction. And you see, the particles of the boiling water are in movement, and because of this movement the heat energy is getting transferred in the water. So this is the energy getting transferred inside the water. Heat energy is getting transferred inside the water. This mode is convection. So in the single figure you can see all the three process: conduction, convection and radiation. Okay, so we are going to explore each of these topics in detail. In the first lecture, in the first chapter, you can say, we will study thermal conduction. So let's see what is thermal conduction. Suppose you are holding some metal rod. Okay, and initially the metal rod is at room temperature. Suppose though this is plastic, for the time just assume like it is made up of metal. So it's obvious that it is at room temperature. Now what you did, you brought one end of the rod over some heated segment, say over a fire. So initially only this end will get heated up. Now what will happen if you're holding this end? Very soon you will feel the warmed state of this end. That is, the heat energy is getting transferred from this hotter region, hotter end to the cooler end. And this process of transfer of heat energy from one point to another point through the medium is called conduction. Okay. Now let's see what is the mechanism of conduction. See, the particles are in vibrational motion. They keep on vibrating with certain amplitude. Getting the point? Inside the substance, the particles keep on vibrating with certain amplitude. When you increase the temperature, the amplitude increases, the vibrational energy increases. Okay? When you increase the temperature, the amplitude increases, the vibrational energy increases. Now what happens in conductor? See, you can write first the definition of thermal conduction. It is the heat transfer between adjacent particles. Particles can be atoms or molecules. So it is the heat transfer between adjacent particles within a substance or between substance and direct contact. Okay, so the transfer can take place within the same substance, or there may be multiple substances in direct contact, but contact must be there. Okay, from a hotter region to a cooler region without actual bulk movement of the material itself. Now see, this is the major difference between conduction and convection. There is no net movement of the material in conduction. Getting the point? It means if there are different particles, they keep on vibrating and they transfer the energy to adjacent particles. This energy is getting transferred in the chain mechanism, and this is how from one end to another end the thermal energy gets transferred. So there is no net movement of the particle in conduction. Okay, so you can write it is the heat transfer between adjacent particles within a substance or between substance in direct contact from a hotter region to a cooler region without actual bulk movement of the material itself. Got it? Now let's see some of the conceptual points in thermal conduction. This occurs through energetic collisions and vibrations. You have seen how the conduction is taking place. The adjacent particles or molecules, atoms, whatever they may be, they are colliding. This occurs through energetic collisions and vibrations where high energy particles transfer kinetic energy. Kinetic energy same as the vibrational energy, where high energy particles transfer kinetic energy to their neighbors, moving heat through the material. Got it? So this is what is happening at the microscopic level without net movement of the particle. Okay, second point is that conduction occurs in all states of matter. Already we have seen in the introduction, whether it's solid, liquid or gases. But it is the most efficient method in solids. Why? Because see, in solids, the particles are closely packed. So they allow faster transfer of heat energy via vibrations. So anytime if you need to answer in which state of matter conduction is most efficient, the answer will be solid. Why? Because in solids the particles are closely packed. So they allow faster transfer of energy via the vibrations. So this is what is conduction, and this is what is happening at the microscopic level in conduction. Okay, now let's see what is the meaning of thermal current. See, we study thermal current and we also study electric current in electricity. First of all, always remember that current is a macroscopic property and property of a surface. Okay, what I said? It is a macroscopic property. Always remember, current is a macroscopic property of a surface. Current is always defined for the surface. We know properties can be of two types. It can be macroscopic or it can be microscopic. Microscopic are the properties which are defined for a particular point. Macroscopic are the properties which are defined for some, you can say, segment of length, some volume, some surface. Okay, so current comes in the family of macroscopic property which is defined for a surface. So whenever you're talking about current, whether it's the thermal current, whether it's the electric current, you have to be clear about the surface through which you have to determine the current. So suppose this is the surface, okay, and through which we have to find the current. So you have to be clear about the surface through which you are going to determine the current. Got it? Now say how the thermal current is defined. Consider a particular surface. Consider a particular surface, okay? And say an infinitesimal amount of heat dq. This is the heat energy is flowing through this surface. Of course, the heat will be distributed over all the surface, not at a point. So this dq is flowing through this surface in a time dt. We are taking infinitesimal time. So your thermal current will be, you can write as thermal current, which is usually denoted by H, as dq by dt. Got it? This is what the thermal current. You remember the electric current? The electric current is the rate of flow of charge. If charge is denoted as dq, so it is dq by dt. The electric current has a unit ampere, and here you see the thermal current will has a unit of, what is the unit of dq? This is the heat energy. The unit of energy is joule, and second, time has a second, so it's joule per second, which is also what? Watt, capital W. So this is the unit of thermal current, okay? Thermal current is also called rate of flow of heat. Remember, thermal current is also called rate of flow of heat. Got it? So this is what is thermal current. You can write heading thermal current or the rate of flow of heat. First thing I told you, current is a macroscopic property, which is a property of some surface. You always define the current or measure the current through any surface. And if a amount of energy dq get transferred through a surface in a time, say dt, then the current would be dq by dt. If suppose you are given a finite amount, so you can write the thermal current as delta q by delta t. Now suppose there is some surface through which a 20 joule amount of heat passes in 5 seconds. So this is what? Delta q, the amount of heat flowing. This is what? The time interval. So the thermal current will be 20 joule divided by 5 seconds. So what will be the answer? 4 watt or joule per second. Got it? So we'll use this thermal current or rate of flow throughout the modes of transfer of heat in conduction and radiation, okay? Now let's see what is the meaning of temperature gradient. You know, whenever you talk about gradient, it means something divided by length. So say you are moving, I'm making a highly magnified figure. You moved a distance dx and the change in temperature is dt. So the temperature gradient, though there is no standard symbol for temperature gradient, but just for the sake of some convection, we will take it as lambda. So the temperature gradient we can define as the change in temperature per unit change in length, that is dt by dx. Got it? Now what will be the SI unit? So the SI unit of temperature is Kelvin, length is meter, so it's Kelvin per meter, and common unit you can also write degrees Celsius per meter, and you know change in the temperature in Kelvin is same as the change in temperature in Celsius. So if you have a temperature gradient x Kelvin per meter, so it will be same as x degree Celsius per meter. Okay. So this is the meaning of temperature gradient. Okay, this is what? Infinitesimal change. If suppose you have a rod of length L and there is a temperature T1 and there is a temperature T2. So delta T will be T2 minus T1. So your temperature gradient will be delta T by delta L. So we'll get T2 minus T1 by L. So instead of infinitesimal, you can also take the finite amount when some interval or finite changes are given. Got it? So this is all about your temperature gradient. The change in temperature per unit length. Got it? The change in temperature per unit length. Okay, now let's see what is the meaning of steady state. See, let's go back to the illustration which I told you in the definition of thermal conduction. We took one picture. Suppose you have a rod. Initially, it is at room temperature, correct? Say 20 degrees Celsius. So each point of the rod is at 20 degrees Celsius. Got it? Okay, now what you did, you brought one end of the rod, say above, steam at 100 degrees Celsius. So this end will be getting hotter and this heat will be getting transferred along the rod from the hotter end. Heat transfer by conduction. Okay, so if you see, say this is a point A on the rod. So what is happening at A? The temperature of A will be increasing with time, isn't it? Say at T1 it was at room temperature of A. At a time T2, since the heat is getting flowed, it came to temperature say 22 degrees Celsius. At a time T3, the temperature came to say 23, and at a time T4, say it came to 24. And say after T4, it became constant at 24. Okay, it became constant at 24. So we say now a steady state is attained. Okay, now a steady state is attained. So what is happening in the steady state? Initially, what will be happening when the heat energy begins to flow? The temperature of a particular point, will be fluctuating with time. Like see, the temperature of the point A is fluctuating with time. But after a certain time, an equilibrium condition is attained for the heat flow. So all points will have constant temperature. I am not saying same temperature. Mind it, I am not saying same temperature. I am saying all the points will have constant temperature. What it means? It means something like this. Visualize. Suppose here you are maintaining the temperature 100 degree. And here say we have ice blocks at 0 degree. And we are maintaining this temperature. We are not disturbing the end temperature. And the steady state has been attained. So what will happen? This point A, okay, I say P, I have taken A this side. P, this will be now at 100 degree. Say A, whatever temperature is of A, say 80 degree, it will be at 80. Say this A is different from this A. This was 24 degree just for illustration. Don't get confused. Here I've taken the temperature of A as 24 degree in steady state. Why here? If you want, I can change the point, okay? Say this point is, I'm making that as Q. Say Q is at 80 degree. This is R at say 60 degree. And this is S at 0 degree. So now these temperature will not change with time. Can you see? So this is the meaning of steady state. If you see any other time, these all temperature will be at their respective values, same values. Of course, if you will change the end temperature, then this temperature will change. So we are maintaining the end temperature. So this is one of the property of the steady state. What? When there is a conduction and a steady state being attained. When there is a conduction and a steady state being attained, then the temperature of any point remains constant with time. The temperature of any point remains constant with time, correct? I'm not saying temperature of different points are same. That is another thing. Number two, what you will see. When the steady state has been attained and you are taking this surface 1. You are taking this surface 2. You are taking this surface 3. So your rate of flow of heat, that is the thermal current. The rate of flow of heat, that is what? The thermal current. That thermal current will be same through each surface. So if here the thermal current is H, here it will also be H, here it will also be H. Okay? And number third property. The temperature gradient will be same along this length. The temperature gradient will be same along this length. That means if you're taking a length of 1 centimeter here, and the temperature change is 1 degree Celsius, and if you're taking a change of 1 centimeter here, so here also the temperature change will be 1 degree Celsius. So in the steady state, we got three properties. What three properties? Number one, each point will have a constant temperature with time. Number two, the thermal current through each surface will be the same. And number three, the temperature gradient over the line of the conduction or the direction of the conduction will be same. Got it? So now formally we can write what is the steady state and what are the properties which are observed in steady state. We can write the heading steady state. Suppose the temperature of the two ends are maintained, that I told you. We are maintaining the end temperatures. Then a steady state is attained. The state at which, number one, the temperature of each point is constant with time, though it is not same for all points. We have already seen this. Number two, the thermal current is same through each cross-sectional area. And number three, the temperature gradient is same throughout the length of conduction current. Okay, now see one thing, in all the problems of conduction, unless stated otherwise, if something else is given that there is no steady state, then the things will be different. But unless stated otherwise, we will assume steady state condition. Got it? We will assume steady state condition. So write all these things. Got it? Okay, now let's say illustration 1.1. Suppose you have a rod, okay, and one temperature of the rod is TH, higher temperature, and this is TL, and the length of the rod is L, okay, and the rod is kept on the x-axis. This is origin and this is positive x-axis. And of course, you're given TH is greater than TL. And we have to plot the temperature versus X graph. See, here I've taken the value of L and here I'm making a dotted line. This is the region of the presence of the rod, isn't it? The rod is between 0 and L. So this is the origin and this is the value of L. So I'm making a dotted line that rod will end at this point. So see, the temperature is decreasing. And right now we have seen in, of course we will assume steady state. Getting the point? We will assume the rod is in steady state. So we have seen that in steady state, the temperature gradient will be same throughout the rod. Right now we have seen. In a steady state, the temperature gradient will be same throughout the rod. What it means? It means the slope of temperature versus length, that is only the temperature gradient. The slope of temperature versus length will be same. So in steady state, remember, whenever in steady state, you plot a graph of length and temperature, you always get a straight line. Maybe with positive slope, maybe with negative slope, depending whether you are going from high to low temperature or whether you are going from low to high temperature, but it will be a straight line because it has a constant slope. Got it? So here we are going from high to low temperature. So what I'm doing, I'm marking the two temperature horizontal segments, higher temperature and lower temperature. Of course, I can't say that this lower temperature will be 0, so I'm not making it 0. I'm marking it above origin. So we will get a straight line and the graph will be something like this. See, this will be your temperature versus X graph in this figure. So always remember, whenever the rod or wire or conductor is in the steady state and you're plotting the graph of the temperature versus length, you will always get a straight line with positive slope or negative slope, depending whether we are moving from high to low temperature, low to high. Here we are moving from high to low, so the graph is going down. So see the next problem. Consider a rod of length 80 centimeter whose ends are maintained at temperature of 20 degree and 60 degree. Okay. So we have a rod of length, how much? 80 centimeter, and this temperature is 20 degree, and this is what? 60 degree. First we have to find the temperature gradient, then we have to write temperature as a function of x. Assuming, suppose it is given in the problem, this is origin and this is x. Okay. So let's see the temperature gradient. So say lambda, that is the change in temperature by change in length. So I'll get 60 minus 20 by 80. So I'll get what? 40 by 80. So I'll get 0.5 degrees Celsius per centimeter. So this is your answer to part A. Now you have to find the temperature of any point at a distance x. Here is the origin. So say you're moving from lower temperature to higher temperature. So when you're moving from lower to higher, the temperature will increase. So say this segment, O to P. The temperature changes delta T. So delta T will be what? Temperature gradient multiplied by x, isn't it? Now temperature as a function of x will be what? The initial temperature, that is what? 20 degree plus change in, why we are adding? Because we are moving from low to high. We are moving from low to high, so the change in temperature will be added. So your answer will be 20 plus lambda x. So your answer will be 20 plus 0.5 degrees Celsius into x. So this will be your temperature as a function of x. Got it? So this is the approach for solving these kind of problems. Now let's see thermal current through a uniform slab. Say, suppose we have a uniform slab. Okay, something like this. And say the area of the slab is A, and this is the length of the slab, say delta x. Always remember, whenever the heat flows, it will flow between two surfaces which will have the temperature difference. Be very much clear about this. Whenever you want to visualize the direction of heat flow, the direction of heat flow. So it will always flow between two surfaces with temperature difference. Flows between two surfaces with temperature difference. Now let's see what it means. Suppose I have a block like this. Okay? And this length is A, this length is B, this length is C. And the left end is at a temperature of 20 degrees Celsius and the right end is at a temperature of 80 degrees Celsius. Okay? So in this figure you can see there is a temperature difference. There is a temperature difference between the left and the right ends. So your heat will flow between the left and the right ends. Okay, this will be the direction of the heat flow. This is how the heat will flow here. But see, if in the same block, if you're taking the same block, okay, and this is what C, this is A, this is B. Now, the top surface is maintained at 80 degree, this is at 80 degree, and the bottom surface is maintained at 20 degree. Now see, the block is same, but the surfaces having the temperature difference are different. Here the surfaces were right and left surfaces, here the surfaces are top and bottom surfaces. So in this figure, the heat will flow vertically. This is the direction of heat flow. Okay, so when analyzing the situation, first step will be you have to decide how the heat will flow. So how you will decide where the heat will flow? You will see the two surfaces which will have a temperature difference. So heat will flow across the surfaces which have a temperature difference. Got it? Number one. Number two, see. Now we will focus. Same thing, will happen in electricity. When you will study in class 12th, there it will be the potential difference. Number two, what you will see? Now you will see, since thermal current or your electric current or thermal current is the property of the surface. So when the heat is flowing or when the current is flowing, it will be crossing the surfaces. Now you have to see what will be the shape of the surface it is crossing and whether the area of cross section of such surfaces is constant or variable. Okay, so decide the shape of surface of current or rate of flow and see if area is constant. This is your second step. You have to visualize this. You have to analyze this. Okay, so say if I am taking this figure, okay, and this length is A, this is B, this is C. This surface, left surface, is at 100 degrees Celsius and this right surface is 20 degrees Celsius. So you will say how the heat will flow. You will say heat will flow like this. Correct? This we have seen as step 1. We have decided that the temperature differences between the right and left surfaces, so heat will flow between them. Now just visualize which kind of surfaces this heat is penetrating. So just visualize that you are taking a knife and you are making the slices along the length of the flow. You are cutting the slices. So your slice will come in rectangular form. Say here you are cutting a slice, you will get B and this will be A. So this is the area of the slice. Correct? Length into breadth AB, through which your heat energy is penetrating. Through which your heat energy is penetrating or heat current is penetrating. Same thing will happen, same analysis will be happening in current electricity. Now think how many such slices will be there. You will say throughout the conductor there will be tremendous number of such slices and each slice is in continuous manner with another slice. Now if you take some slice anywhere ahead, can I say I will get the same dimension of the slice? Yes or no? Say I am taking a slice here at a location 1 and then I am taking a slice here at a location 2. So again you will get the cross section as a rectangular cross section with the same length and breadth. Yes or no? Yes. Same area. Okay. So in this figure what you can say, of course the heat is flowing perpendicular to the surface. In this figure what you can say, the current is flowing through uniform area. What? Uniform cross-sectional area. So you can have two cases when you are studying the flow of current. Either the area can be uniform like in this case or the area can be non-uniform. Okay? And here the length of flow, this will be the length of flow. what is the length the heat will travel inside the conductor, so it will come to be C. Now see the next illustration. Suppose you have a hollow cylinder, something like this, okay, a hollow cylinder. And this is the axis of the cylinder. And say the inner radius is A and the outer radius is B. And this end is maintained at 100 degrees Celsius. This end is maintained at 20 degrees Celsius. So can you tell me, step 1, between which surfaces the heat will flow? Between which surfaces the heat will flow? So we'll say, clearly we can see there is a temperature difference between the right surface and the left surface. So the heat will flow between the right and left surface. So this will be the direction of the flow of heat, parallel to the axis of the cylinder. This will be the flow of heat, number 1. Okay, number 2. Can you tell me, just visualize, cut a slice along the direction of the flow. Cut a slice perpendicular to the direction of the flow. You're moving along the direction of the flow, cut a slice, okay, something like this. So you're cutting a slice perpendicular to the direction of flow. So can I say the slice will be something like this? So what is the area through which heat is flowing? Heat is flowing perpendicular to this slice. So what is the area through which heat is flowing? You will say the area is pi b square minus a square, correct? Now tell me, when the heat is flowing in this conductor, is the area uniform or non-uniform? Just think and answer. When the heat is flowing in this conductor, when the current is flowing in this conductor, the area is uniform or non-uniform? So you can cut the slice anywhere, you will get the same slice. So of course area is uniform. Got it? So these are the illustration where the current is flowing through uniform area. Okay, now see another illustration. Suppose we have a hollow cylinder. The same cylinder. Now you are maintaining the temperature difference between the inner end. This inner end is at 100 degree and this outer end is at 20 degree. Now see the difference. And the inner radius is A and the outer radius is B. Now tell me, in this figure, the temperature difference is not between the right and left surfaces. The temperature difference is between the inner cylinder and the outer cylindrical surfaces. So how the heat will flow? So now the heat will flow between inner surface and outer surface like this. Flow will be radially out, correct? Your flow will be radial. It may be in or out. In this case, it will be out because your inner surface is at higher temperature. So now just visualize what will be the shape of the cross section through which heat will be flowing. So just imagine a coaxial. Coaxial means same axis. Coaxial cylinder. This is a coaxial cylinder of radius r, okay? Coaxial cylinder of radius r. Now heat will be penetrating. Though it's appearing a 2D figure, but basically it's a 3D figure. Heat is going radially out through the curved surface of this cylinder. Heat is radially out, or it may be in case if the outer temperature is high. Heat is flowing radial to curved surface of this cylinder. If you see the cross-sectional view, So this is the inner surface, this is the outer surface, this is A, this is B. Okay, and this is the direction of flow of heat, radial, and this will be the cross-sectional surface of your cylinder R, cylindrical surface, and say the length is L, length of the cylinder. Now can you tell me what will be the surface area through which thermal current is penetrating? What will be the surface area through which thermal current is penetrating? So you'll say, since it is penetrating through this yellow cylindrical surface, so we'll have to take the surface area, curved surface area of the cylinder, curved surface area of cylinder. So it will be what? 2 pi r L. So this will be the area in this case through which current is flowing, 2 pi r L, through a cylinder of radius r. Now see in this figure what you can judge. As the heat is flowing between the inner and the outer curved surfaces of cylinder, as the heat is flowing between the inner and the outer curved surfaces of the cylinder, the area of cross section is constant or variable? Think and answer. The area of cross section is constant or variable. So since for each cylinder R is changing, so your area is changing. So in this case the area is variable. Got it? So in this case the area is not constant. So see, the same cylinder, when it was having a temperature difference between the right and left surfaces, heat was flowing through this slice. So heat flow was through a constant or uniform area. If the same cylinder is at a temperature difference between inner and outer surfaces, then heat will flow between the inner and outer surfaces and area will be variable. Now as a homework, just think about a sphere. As a homework, suppose we have a hollow sphere. We have a hollow sphere, okay, say with inner radius A and outer radius B. Got it? And this inner surface is maintained at say 80 degrees Celsius and the outer surface is maintained at 20 degrees Celsius. So what do you think, where the heat will flow? So heat will flow radially. Again in here the heat will flow radially between the inner and outer surfaces. Now what you have to do as a homework, number one, make figure of surface through which heat is flowing. Number two, write its area A. And number three, tell heat flow is through uniform area or non-uniform area. Three things you have to tell. Okay, this you will submit me on Messenger. We'll send the answer. So we have seen whenever the heat is flowing, first step you have to visualize the two surfaces which have a temperature difference. Got it? First thing you have to visualize is what? The two surfaces which has a temperature difference. Number two, after visualizing the two surfaces which has a temperature difference, you can determine the direction of flow. The flow will be between two surfaces maintaining the temperature difference. Then you have to analyze during the flow the direction in which the heat is flowing. Is it crossing a uniform cross-sectional area or non-uniform cross-sectional area segments? If each slice has the same area, like in this figure, then we'll say the heat is flowing through uniform cross-section. And if the area is getting variable, then we say the heat is flowing through non-uniform cross section. And as I told you, same thing will be applicable in your current electricity. Both the topics are very symmetrical. For all thing resistances like will determine the resistance of these cylinders and sphere. Same formula will be applicable in current electricity. So the thermal current flows between the surfaces. This is very much clear. When the thermal current flows, the area of penetration of flow may be uniform or non-uniform. This already I told you very in much depth and detail how you have to visualize the area of flow, whether the area is uniform or non-uniform. Correct? Now we will see what is the formula for thermal current through a uniform slab. Uniform slab means the area is uniform. And say we have two surfaces. Here the temperature is T1, this surface, left surface, and the right surface has a temperature T2. I don't know which temperature is higher. So here you see what will be the direction of flow of heat. So you will say, sir, it is very clear since the temperature differences are between the right and the left surfaces, so heat will flow in the horizontal direction, isn't it? Either towards right or towards left, depending which temperature is higher. So for the time being, say T1 is greater than T2, so heat will flow like this. Now experimentally, it is found that, number one, that we are talking about rate of flow, remember. We will talk about rate of flow, H, that is delta Q by delta T, or you can say dQ by dt, thermal current. So experimentally it is found that this thermal current is directly proportional to the area of the cross section, number one. Higher the area of cross section, higher will be the thermal current, higher will be the rate of flow. It is found that this thermal current is directly proportional to the temperature difference. Higher the temperature difference, higher will be the rate of flow. And it is found that this temperature difference is inversely proportional to the thickness or length. Here it is inverse proportionality. That is, more the thickness, lower will be the thermal current. So you know, when you have houses with thick walls, this is to reduce the leakage or incoming flow of heat. The rate of flow will decrease. If we combine all the three equations, we will get the rate of flow is proportional to A delta T by delta X, correct? Now, of course, if you have two walls, okay, with same temperature difference, with same thickness, with same area, but one is of iron and say one is of wood, the rate of flow will be different in the two material. So apart from these three parameters, there will also be a role of the property of the material which will decide the rate of flow. So when we remove this proportionality, we introduce a proportionality constant K. And of course it will depend on the property of the material. So we can write this equation as the thermal heat or rate of flow, where K is called thermal conductivity or coefficient of thermal conduction. Okay, this case called the thermal conductivity or the coefficient of thermal conduction, and it is basically the property of material. This is not the property of the object, it is the property of the material. Like your iron will have some different K, your copper will have some different K, okay? Higher the value of K, better will be the conductor. And let's see what will be the unit of K, SI unit of K. So if you make K as the subject, you will get the thermal heat multiplied by length divided by area change in temperature. We have seen thermal current has a unit watt, length is meter, meter square Kelvin. So this will come to be watt per Kelvin meter. Watt per Kelvin meter, which can also be written like, this is basically the SI unit, and the common unit you can also write watt per degree Celsius meter. So this is the unit of K. Well, also see, as in electricity, we define electrical resistivity. Same thing here will be thermal resistivity rho. This will be 1 by K. Okay, and it is also the property of the material. Always remember, resistivity and conductivity are the properties of the material. But when you talk about resistance or conductance, these are the properties of objects, not of material. Getting the point? So like you have two copper slabs and both have different area, different length, etc. So they may have different resistances. They may have different resistances or conductances, but their resistivity will remain the same, because resistivity is not the property of the object. Clear? Resistivity is not the property of the object. Same resistivity, same conductivity. Got it? So these two parameters are the properties of the material. You know, so many times you have seen there are some properties which are of material and some properties which are of objects. So this is the formula for thermal current. Now basically when you apply this formula without sign, so this will give you the positive value if you are applying this. So you will always write Ka, higher temperature minus lower temperature, divided by the length through which the heat is traveling. Got it? We will see right now. When we apply with sign, then what will be the difference? Now see, thermal current equation without sign when you are applying. So suppose this is the slab, and the limitation of this equation is, remember, this is applicable when the area of cross section through which heat is flowing is constant. So this equation without sign, you will write K A delta T by length or delta X, whatever. And remember, there is a limitation of this equation. This must be applied for uniform area. So say this length is L, this temperature is 20 degrees Celsius, this temperature is 80 degrees Celsius. This area is A and the conductivity is K. So from the figure, you can tell very clearly where the heat will be flowing. You can say the heat will be flowing from the right surface to the left surface, because this is at higher temperature, this is at lower temperature. So this will be the direction of thermal current, isn't it? So if you are applying this equation without sign, to always take delta T as higher temperature minus lower temperature. Mind it, very important. Always label at higher minus lower. So here your heat of flow will come to be Ka. What is higher? 80 minus 20 divided by L. So I'll get Ka 60 by L. This will be the answer. Okay, so whenever you are applying this equation with a positive sign, so delta T will be higher minus lower. Got it? Okay. Now see, basically when we write this thermal current equation with sign, this is very important. Then the equation is written like this: minus Ka delta T by delta X, or minus infinitesimal amount dt by dx. This is the equation with sign, and this will give you both the magnitude of current as well as the direction of current. Okay, magnitude of current as well as the direction of current. So this is very important article, how we apply this equation with sign. Now what is the significance of negative sign? Here the significance of the negative sign is that current flows along a direction of decreasing temperature. Okay, the heat or thermal current or heat flows in the direction where temperature is decreasing. So let's see how we apply this equation. Suppose we have a rod, okay, and this temperature is Tx and this temperature is Ty. Now we don't know which is higher temperature. I don't know which is higher temperature. We don't know which is higher temperature. Got it? So same like in the previous figure, it was much clear from the figure that heat is flowing from 80 degree to 20 degree. So we have applied this equation and put higher minus lower, and we are not putting minus sign. See, be careful. Here we are not putting any minus sign. No minus. So when you are putting no minus, you will take delta T as higher minus lower. Now I am going to apply this equation. As I told you, this equation will give you both the magnitude of current as well as the direction of current. So what is the step 1? Label any possible direction of current. What is the meaning of possible direction of current? This is for sure that it is the left and right surfaces which have the temperature difference. So either the heat can flow from left to right or from right to left. Now this is your choice where you label where you want to label the direction. So say I am labeling the direction like this, from left to right. So this is I am labeling as heat flow. Say H. Okay. Now algebraically 3 possibilities are there. I will apply sign equation of H. If H will come to be positive, so it means where I have labeled the actual flow will be same. So the actual flow will be towards the left side. If H will come to be negative, it means where I have labeled the actual flow will be opposite to it. So the actual flow will be towards the right side. And if H will be 0, there will be no flow. Clear? So this is your step 1. You can label the heat flow in any one of the possible direction. Clear? You can label the heat flow in any one of the possible direction. Number 2. Delta T in the sign equation will be taken as final temperature minus initial temperature. Mind it, not the higher minus lower. Not higher minus lower, rather final minus initial. And how you decide final and initial? You are moving towards left side. So when you are going towards left side, this will be your initial point. So this is the initial temperature, this is the final temperature. So in this figure you will get Tx minus Ty. Had you been going towards right, then this would be the initial and that would be final. So your delta T would have been Ty minus Tx. Now write heat is equal to minus Ka delta T by change in x, and say this length is L. So this will be the change in x. So we'll get minus Ka Tx minus Ty divided by L. So this will be your answer. Now depending on Tx and Ty, it can come to be positive or come to be negative. Now see the first possibility. Tx is greater than Ty. So Tx minus Ty will be what? Positive. So your H sign will come to be negative. So you have labeled H like this. So it means your actual flow will be towards right side, and it must be towards right side because you can see Tx is greater than Ty. So heat will flow from higher to lower temperature. Case 2, Tx is less than Ty. So Tx minus Ty will come to be negative. So heat flow will be negative of negative will be positive. So you have labeled H left side, and since it is coming positive, so actual flow will also be left side. And can you convince yourself it must be left side? Because why is that? Higher temperature than X. And of course case 3, if Tx is equal to Ty, delta T will be 0. So your thermal current will come to be 0. Got it? So this is how you apply the equation with the sign. You always put a negative sign and you will take delta T as what? Final minus initial. If you see a very simple illustration, see this. So this temperature is 20 degrees, the same problem which we did with positive sign equation. Conductivity is K. Okay, where the heat will flow, you will say, sir, it's very clear. heat will flow from right surface, which is at higher temperature, to left surface. But I am labeling, since I'm free to label, I'm assuming that heat is flowing in this case towards right side. Let this be the heat flow. Now tell me from your common sense. Tell me from your common sense, if I'm taking in this figure the heat flow as from 20 degree to 80 degree, what must come to be the sign of H? Must come to be what? Negative? Yes or no? Because here you can see, intuitively you can say, heat will be flowing from right to left, and I have labeled left to right, so it must come to be negative. Now let's see. We will apply the sign equation, minus Ka delta T by delta X. What will be delta T? Final minus initial. What is final? So you are traveling like this. So this is your initial point, this is final point. So you'll get 80 minus 20, so you'll get 60. So H will come to be minus Ka 60 divided by delta XL. So see, this is positive, 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 positive. So this is coming to be negative. So negative sign is telling you, you have labeled the heat flow towards right. Actually, the heat will be flowing towards left. Got it? So I guess now it's clear how to apply the equation with the sign, applying the equation of thermal current with algebraic sign. So this is your lecture 1 of thermal conduction. Now we'll continue in lecture 2, and in lecture 2 we'll be doing the problems, how we apply this equation, how we will find the resistors in series, how we'll find the resistors in parallel, how we can find the temperature of the interface of two slabs, how we can find the temperature of the junction of three rods. Okay, so we'll meet in second lecture of thermal conduction.